Okay, so here we are in the lab again, and so this is episode number 3 of Build Your Own IDE Disk Emulator. And this project, it started out just as going to be an SD card as a hard drive and like a micro SD for the floppy. Seemed like a good idea. Found out later that it's not a good idea because those kinds of storage devices can't be written to and read, or read and written to continuously like a hard drive requires. You could do it for a floppy, but the hard drive, the memory would get written to too many times, and it damages it. So in a real SD drive, an SSD, uh, the has a special built-in controller and algorithm that reads and writes to it spreads it out across the drive, so no position gets written to too many times. Um, so so that evolved into me finding out about the CF card. So the CF card is basically designed as a solid state IDE hard drive. That's pretty much it. And it's just a plug and play. You can just get an adapter, plug in your CF card, and plug it right into your IDE controller, and you can go. Like in the last video where I showed you how to connect it, just like that. That's exactly the way it was intended to be used. Okay, so now the concept is you can use it like that, and that's fine. But I want to go a little bit farther. So instead of these SD or CF cards, they just pull in and out of their socket. All right, so you can use that as removable storage. So with an IDE controller, you can have 2 hard drives on one IDE controller. So it's what I plan on doing over here with my computer. Is I'm going to use a CF card for the hard disk, but I'm going to also use the CF card to replace the floppy. So and that's a win-win, because you have just one controller and you eliminate, well, you take care of 2 things. You take care of the hard disk for the boot up and all that stuff, and you also take care of solving the removable storage issue. And not only is it like removable storage, but it's like 1-2 gigabyte, whatever you can get your BIOS to use. And so you can just pull it out, use that for the like drive D, and you can just pull that out and you can pop it into your little CF adapter on your main computer or some other place, and write a whole ton of files to that thing, and bring it over and plug it into your old retro computer, and you have a large amount. You have like a 2 gigabyte floppy. And that's really cool for an old 1993 retro computer. So that's the way I'm headed for this. So last time I showed you that this my card had a whole bunch of wires on it, and I took all of those off, and now we have this add-on card that I had made at PCBWay, and you can see it's just a header that connects all the edge connectors to this card, and we don't use all of them. We'll go over which ones we use. And so I said that it didn't work before. I said that it worked, but then it didn't work at the same time because it wouldn't boot up. So I found the problem. So the problem is, at least on my computer with the 386 BIOS, I don't know if all BIOS is that way. I don't know if the 8086 does it or the 286, but mine requires, when it boots up, the BIOS checks the controller, and it requires an IRQ 14 for the primary and an IRQ 15 for the secondary. So if it's going to make it past the discovery part of the BIOS post, then it has to have an IRQ, and that was my problem. So as soon as I hooked up the IRQ, then that's what this wire is right here. Is this is my IRQ wire, because I wasn't sure that it was going to work. So I put that on there, and it started working. And then these other wires here, ChatGPT recommended that I control the direction of the 245 buffers separate than using the read line from the ISA bus here. All right, so the read line goes up to the IDE, and but now I don't know if that didn't fix it, obviously, but I don't it. I'm gonna roll with it, because with the decoding chip controlling the direction of the buffers, then you have the power over reprogramming the chip, the decoder chip, and changing it if you need to. So you have that option. So this is going to change, and I'll put up the schematic for all of the change, and should be able to just have the board made and plug it in. So then the next step is we're going to take a microcontroller, and I'm going to take this microcontroller off. We're going to use one with the USB. So now that's the next step. All right. So the next step is to take a USB and microcontroller. And so the microcontroller will interface with actually more than one USB port, because as well I envision, I like my wireless mouse, I like my wireless keyboard, and it's always good to be able to plug in a jump or a flash drive or some other USB. So there's going to be at least 3, maybe 4, because there's never enough USB ports. So we're going to have up to 4 USB ports on this card, and I think we'll have to have a slot here for a for the USB, just to plug onto here. So that's going to take some work, some machining and stuff. But anyway, so what I envision is 4 USB ports hooked to a microcontroller that processes the information. So whatever you stick in there, it's going to read the USB, determine what it is, and then if it's for a mouse or a keyboard, for instance, if it's a mouse, a wireless mouse, it's going to read the USB data, process it, and then it's going to send it to the ISA bus as a serial port. Okay, so when the BIOS or the computer reads to address, what is it, 378 or something like that, for the serial port, then it will be reading that USB on the mouse. Okay, and the same thing with the keyboard. So instead of being a serial port, it'll be the keyboard. It'll be, I guess it would still have to be serial, but might have to have a driver for that. That might get some kind of tricky, but I want a wireless mouse, wireless keyboard, and then some other USB ports for storage or whatever, right? And so I think for the SD or the CF card, I think it'll just go in the place of the floppy. I think we'll just have it like a floppy, but you just pull it in and out of the front of the computer. I think we can do that. And so let me go over some of the more details of the card, how we interface it. We'll go over the schematic, and then we'll write some assembly code so that you can see how we test to see if the card works properly. All right. So the next up, let's check out the schematic. Okay, so here's the schematic, and you guys can bash me all you want on the schematic, because I don't spend a lot of time on the schematic, because since it's in Fusion and it's directly connected to the PCB, I just get the parts on there, get them connected together, and if it looks good, it does. If it don't, it don't. And there's some, weird connections that could be like make it more beautiful and stuff, but I don't usually worry about that too much. So this is what you get. Okay, so this is what we got. We have down here, we have the ISA bus. All right, so these are the signals that we use. So we use all the address lines up to A15. So we use 16 address lines, and this is just kind of standard decoding, because you can, that means like these upper address lines, that means you have like you can write to these upper address lines with this address as a base address and still address it. But the idea is that your BIOS doesn't access anything above that, so you don't really have to worry about it, and it saves on decoding logic, and it's been done like that for many years. Got our address lines. Then we have 8 data bit lines here, and so then we have 16. We have to do 16 bits for the CF card. IDE standard has 16 bits, but only for one register, and that's the data register that transfers the data, actual data from the drive to the CPU. So, but we still need 16 data lines, and so that's right here. All right. They call it SD on the ISA bus, so SD through SD15, SD8 through SD15. All right, so then we have all the address lines, we have the data lines, and so then there's an address enable here. So the AEN, the address enable line, indicates that the microprocessor is accessing a regular I/O transfer or a DMA. All right, so when it is low, that means it's normal. When it's high, that means it's a DMA cycle. All right, so you have to include that in your decoding, or it'll mess things up, it won't work. All right, so then, let's see. We have a ground and then our 5 volts to power our chips. And everything on this card is 5 volts right at the moment, but that's going to change later. So we have our reset, and we have to run our reset through the decoding chip to invert it, because for some reason IDE and the CF card requires an active low reset, and this is an active high reset that comes off the ISA bus. So it has to get inverted before you can use it, route it to the IDE. Another ground, you want to tie in a lot of grounds and powers and use caps to decouple it, keep the noise down. Then we have I/O write and I/O read, which is self-explanatory. When they're low, when I/O read is low, it's reading, it's requesting data, and so that means the data is coming from outside into the computer, into the CPU. And okay, and then write is just the opposite. When it's low, you send in data from the CPU out to your CF card or whatever else there is. Okay, and then we have this, which is an active low signal, IO chip select 16, and that indicates that you're in a 16-bit cycle. All right, so in order to read 16 bits, the device that you're reading has to pull this low to tell the CPU to read 16 bits. Otherwise, it does either one 8-bit or 2 8-bit read cycles, which if it can cause problems if you don't have this IO chip select 16 set up properly. And that just goes over. Let me hit my eyeball here. All right, so it goes directly to the IDE. So we'll get up there in a minute here. We've got a couple more lines. So then this is your IRQs right here, IRQ 15 and 14. 14 is the primary IDE controller, and IRQ 15 is the secondary IDE controller. And so then that's it. That's all the signals that we need to make the IDE work. All right. So you have to buffer your data. You should never connect the bus directly to your project because things can happen and it'll stop your bus. Or I've never done it, but I guess you could actually damage the computer. So we have normally we have two 74LS 245 bidirectional transceivers, 8 bits each, but I am using 74LBC8T 245, which is behaves identical to this LS 245, but it has dual voltages. So you can set it up to where this side over here is a voltage, like 5 volts for ISA, and we're going to do this later. And then so you can have this side as 3.3 volts, or whatever you supply it with, but we'll have 3.3 volts. So that way we can interface directly with a microcontroller, all right? And the CF card can do either. It's set up to, it can run 3.3 or 5 volts. So that's very convenient. So these send the data to the IDE in and out, dependent on the read signal. Okay, so then this is the IDE connector. This is your key where it fits in, and then this is a key pin. Usually that pin is missing. All right. So then here's your buffered inverted reset signal. And then your data bits come through your bus transceivers, the 245s. And so then you have your I/O read and write. That goes directly to the ISA bus. So does A0 and A1, so it can select the registers inside, and A2, because there's 7 registers in your IDE drive. Regardless of what kind of drive it is, it has 7 registers. Actually 8 registers if you count the secondary register. We'll get into that. All right, so then you need chip select 0 and chip select 1 for the IDE for the CF card. Then you have C select, which is your master slave select. All right, so we have a jumper here, and it either opens it and connects it to VCC, or it shorts it to ground for the master. All right, and so then we have our upper data bits here, and that's pretty much it. There isn't much to an IDE. We have our LED indicator when the drive is active. All right, so it is active low. So you connect the anode to VCC and the cathode to the pin 39, and that will light up whenever the drive is active. Now the chip select 1 and chip select 0s are for the register block. There's a control block and a status block. And then the A0, A1, and A2 select the specific register. And we're going to get into that too in our programming and stuff. All right, and so that should be all of the ones. Did I miss anything? No, that should be everything that we need. The output enable, which turns on the pins. So you can have the direction set, but if the output enable of the buffers is not enabled, which is low, there won't be any output on the bus. That's specifically to isolate the peripheral, your project, from the ISA bus, so it doesn't can interfere with other operations going on. All right. So that is controlled by the decoder chip. So we went over the decoder chip in the first video and the CPUL code. So we don't need to go over how we program it and stuff on this one. But it is set to do the direction when the correct address is selected. And so that triggers the decoder to come out here, and then your direction is controlled by the decoder as well. So if it's a read, then it goes one direction from here to here, from the B side to the A side. And if it's a write, the data goes from the A side to the B side. All right. So it's fairly simple. There isn't a lot to this. So the decoder chip, it uses all the lines on the decoder chip. I was hoping for a few extras, but that's okay. It seems to work real good. And so that is our schematic. Oh, and I forgot about this jumper I just added in. This is the IRQ jumper. That just connects the interrupt request line on the IDE port to the IRQs down here. And so you can move the jumper one side or the other, and one's for primary IDE and one's for secondary IDE. And that just gives the option, you can put 2 of these in, and you could run 4 hard drives if you wanted. I probably won't. I think 1 should be enough for my application, but who knows what other people need. So you can either like just do away with that and connect it directly to IRQ 14 for primary, or you can do the jumper. It's up to you. That option is there. And so that's it. That is our schematic. Okay, so that's the schematic. So now let me just pop up the CUPL file for the programming of the decoder chip that we went over that in the first video, but so I'll just pop that up real fast, and then you can see it changed a little bit, but some of the pins and stuff, and the whole idea is the same. There's nothing changed on that. So then let's take and stick this card in here and boot it up, and then we'll look at some of the registers inside, and that's how you test to see if your decoding and stuff works properly. All right, so we're going to take our card right here, and we're going to go in here, try not to knock the camera down this time. We just plug that in there. The red line is always pin 1. So we got to get that guy in there like that. All right, so there's our cable going to our CF card over here. All right, we just plug this in the first slot like that. All right. Okay, so that guy's in there. And now we can turn on the power. Power on. Okay, and we are booted up. So that is the CF proto card. Yeah. Okay, so if you want to test your hardware, you're going to have to like put in your regular factory controller and hard drive and all that, and then put your card in alongside of it, but address it with your decoding chip, address it for the secondary controller, and then you can do the same reading and writing we're going to do right alongside. And this will be the same, except the address will be a little different, and we don't have a factory controller in, we just have our proto card. So the first thing you want to do is go into the DOS, the built-in DOS debugger. So hit debug, enter. That puts you at the debugger prompt. And we just want to read the status of the drive. So the drive status register is at address 1F0 for the primary and 170 for the secondary. All right, so we're on the primary. So we just want to go in to read it, and then our port is 1F7. Okay. Enter. And so 50 is what you want to see. 50 means the drive is idle, it's ready, no errors, everything's good. You want to see 50, all right? So one issue is the debugger only does 8-bit reads and writes, okay? So what we want to read next is we want to tell the drive to identify itself. So there's a command called identify drive, but when you read the data, it's 16-bit data, so we're not going to quite get to 16 bits in the debugger. But I'll show you how to do the command. So we'll do out because we're sending it out. So we're going to send it to register 1F6. And we're going to send a hexadecimal A0. And in debug, everything's hexadecimal, so you don't have to tell it specifically. So A0 just means that you want to talk to the master, because you can have master or slave, right, on each controller. So if you want to talk to the master of the primary IDE, all right? And then you want to send the command of identify the drive, right? So that is out, and that's at 1F7. But since we're sending a command out to 1F7, it is not the status register. Status register, when you read it, it is a control block register when you write, okay? So we're going to write 1F7 EC. That's the command for identify drive. Enter. So then you see that the drive LED lights up. So that means the drive is ready to receive data and to send data, right? It's ready to rock and roll. So identify drive means that you are going to read 256 words from the drive, and then once you do that, the drive will turn the light off and go back to the status 50 up here. All right? So we want to read from the data register, which is 1F0. Whoops. 1F0. All right, 8A. Remember 8A. You can write that down. All right, now we're going to read it again, because remember, this is only 8 bits. That's all we can do here. So maybe if we read it again, we'll get the other 16. Maybe not. Let's try it. In 1F0. So that's 94. So remember that number as well, because we're done in debug for right now. So we'll just Q for quit. Back to the C prompt. Okay, so now I have installed the Microsoft Assembler on my computer here. So it has its own interface, kind of like DOS shell in the old days. But it's called Programmer's Workbench, which is PWB. And and that loads the assembler interface. All right, and you can't even use a mouse on here. It's just strictly old school. All right, so first we start out with 8086. It just tells it that we're not going to use any extended register set, no 32-bit registers, nothing that a regular 8086 can't understand. So it's 8 and 16-bit registers. All right. Then the model is the small memory model because it's not doing a whole lot of anything. The stack, we're defining a stack at 100 hex. All right. Or in size of 100 hex. And so this is the data segment. That's the stack segment, data segment. And I'm defining a 256 word buffer here, but I'm not using it right now. But it's defined. It's ready for my next thing here. And so this just moves the address of this data buffer into AX, and then we copy AX into the data segment. And you have to do that in assembly because AX is always the working register for moving data. You load that first, then you move the data into whatever register you want. You can't normally just take a value and stuff it into the DS register. Like you can't go move DS OX5 usually. Depends, but not usually. So you move it into the AX first, then the DS. All right. And we don't even care about that right now anyway. So the first thing you want to do is push all the registers. So I probably should do that before here. But we want to save all our registers onto the stack so that when we finish our program, we pop them off, and then the registers are the same as before we ran our program. All right, because we're going to change those registers, and maybe the system depends on some of those registers for what it's doing. All right. So the first thing is to select the master. That's the same commands that we did in debug. All right. So we move AL. So every register, AX, DX, BX, everything has a low register and a high register for the upper and lower 8 bits. Because each register DX, AX, those are 16-bit registers. So when we're writing to the registers, we always want 8 bits except for the data register. The data register 1F0 is the only register that has 16 bits in IDE. All right. So other than that, we want to do 8 bits. So that's when you do the AL. That tells the processor you are only writing 8 bits. Okay. And it only sends out 8 bits. All right, so we load the port address into DX. We load the command for the master to select the master, and then we out the port and the data onto the bus. All right, and then we do the same thing we did in debug with the command at 1F7 and EC, and we use the AL because it's 8 bits as well. And now one thing that we do here that we did in debug is that you can't read and write to the drive until it's ready. So we pull a couple bits, which that's the test. We test it, and if it's 0, it jumps through, falls through. If it's not 0, it keeps repeating until it is 0. All right, so that means it waits. So we have the DRQ has to be 1, the busy bit has to be 0. And so once the DRQ is 1, we come down here and test for busy. If it's 0, then we go back up here and we wait. All right? That doesn't sound right.
test AL8, jump on 0 to here. So if it's 0, we have to come up here. All right. If it's not 0, see this one's not 0 and this one's 0. So this is 1 and that's 0, so they're opposite. It falls through when the drive is ready, okay? And so then the number of words that we read is 256. We put that in the SI register, and that's just an available register, nothing special about it for us anyway. And so this is where we start reading the words. And so basically the only thing that happens is we load the port, we read the port, we save the data that we read onto the stack, we copy the data into the BX register, and we move how many bits we're going to shift it right. So this is however many bits we're going to shift. We put it in the CL register, and we shift it right, and that takes the very upper 4 bits of the 16 bits and pushes it down to the lowest 4 bits, and then we compare it to 9, and we jump if it's not equal, we add 7 to it, and this is just converting it to digits, and because you need to convert it from 0 to 9 for decimals, and then we got to convert it to an ASCII character by adding 30 hex, and that's what the 0, the character 0 is 30 hex. And then we move the command, a command, into a H, because we're going to call interrupt 10. It's a BIOS interrupt. It means to write to the console, these two together. And we're going to write what's in AL. So when you call this, anything in AL is what's getting written. All right, so then we bring AX back that we saved, and we do repeat that for all 4 digits. And I'll have this listed so you can download it. All right, so then we come down here and we put a space. I write a space in between loops just to separate the words. And then every time we loop, we decrement that SI. So as long as it's not 0, we keep looping, and when it's 0, it falls through and we terminate the program. We pop all of the registers back to the way they were before we started, and then we call BIOS interrupt 21 with the 4C in there, and that terminates our program. If you don't do this, your program won't terminate and you won't get back to the C prompt. All right, so we'll exit out of here. So there you create your assembly program. So now you have to assemble it into an object file, and then you have to take your object file, which can have many object files or just one object file, and you link it to each other and to any libraries or whatever you want to make your program with, and create either a .com file or a .exe file. And so we're going to do an exe. So the way you do that, first we assemble it by using MASM, which stands for Microsoft Assembler. And our program name, our file, is drive0.asm. So as long as you name it .asm, then you don't have to specify a file extension, because that's the default. So this is what it actually does using these command line switches. And see, that's our program .asm, and it assembled it. All right. So then we have to link it, and we use the linker, and we drive 0, and this creates an OBJ, and that's what link looks for. So we just hit enter because we didn't tell it anything else. and we want to do a drive 0 exe. If you want to change the name or the extension or whatever you want to call it, you can do that here, or you can just hit enter for the default. And there's our map file, and any libraries will be listed here that we want to add, and that's our definition file. If we want to create a definition file, then we'll change that name. All right, so there's our, we should have created our drive exe. If there's an error in the process, it'll let you know and tell you what line number. So now we should be able to just type drive 0 and it should execute. Okay, so there is our 256 words, and you notice the light went out on the drive, so everything worked perfect. So now back to the numbers that I had you remember. So when we read from 1F0, the data register, the first time, we got 8A. So we read it again to see what would happen, we got 94. So each time it's an 8-bit read, but we're not getting the full data. Okay, but so when we ran this program, it does 16 bits, and so it got the full words. And so most of this data is manufacturing stuff, serial number, all that stuff, but this is what we want right here, 848A. That is specifically reserved to indicate a CF drive, okay? And so if you get that on your card, you're 100% A-OK, because that, if it can read that, it should be able to boot up, do anything.
Okay, so there you go. That is the first stage in this project. So the next thing is I'll start getting a microcontroller together, and we'll get it stuck on there and get some stuff hooked up, and see if we can get the USB going. And as far as the CF card is concerned, it's pretty much developed. I think there's not much to the IDE. It's just some buffers, and that's about it, and some decoding. So that's about it for that. And so I guess the next stage is some USB, and that's going to take some programming. You got to program the USB, and you have to process the data coming in from the USB, and then you have to emulate a serial port if it's for the wireless mouse, which is the first thing I'm going to try to do, is the wireless mouse. So that's pretty much it for this one, and I will see you in the next video.